Okay, okay, good morning, everybody. And before starting, I wanted to say that you can ask questions in any language that I understand. In particular, those from São Paulo, Brazil, they can ask in Portuguese, and I will translate it to English. So maybe, okay, so let's say the direction problem, orientation. Okay, so let's start the second lecture. Any question regarding the first lecture? During the course, we will be back to integrals often, because the idea is that we want to understand integrals, and we will learn a lot of algebraic topology and algebraic geometry. But for us, the main product is the study of integrals, and not the pure statement in algebraic topology or algebraic geometry. Anyway, and the idea is that we want to learn also basics of algebraic geometry. And okay, let me start. So okay, so let's remind what is our main variety, or our main topological space. This is the projective space Pn, and so this is the set theoretically. This is the space of one-dimensional vectors. One-dimensional vector spaces in Cn+1, and if you want, you can see it also as Cn+1 minus origin, modulo equivalence. And what is this equivalence? 2 points are equivalent if and only if one is the multiple of the order. There is a k that x equal to k for some non-zero complex number. So remember this notation: C star will be for us C minus 0. And okay, this is let's say this is our main object. If you want, okay, as I said, you can make figures. So x, these are the lines passing through the origins, its points. Later, we will use affine chart for this projective space, because most of our integrals that we want to study in the course, they are written in the affine charts of projective space. Okay, so maybe again, let's fix our notation once for all. A point in Pn, we will denote it by x0 2 point, x1 2 point, and until xn. And this will be our notation. And I will switch between. I will use also the same x for points in Cn+1, just for simplicity. Okay, so this is our first, let's say, topological space that we need, and the others are just subvarieties of this projective variety. So let's I'll explain very fast this one. So we are interested on projective varieties. So what are projective varieties? We have to take a homogeneous polynomial f1, f2, fk in Cx. Just remember that this x is for us is multivariable, so it will be x0, x1 until the x capital N. If you take this homogeneous polynomials f1, f2, fk, then simply you can form this the variety x, which is basically the zero set of f1, f2, fk. All the points in xpn, such that f1x, f2x, fkx is equal to 0. And so you see that here x is defined up to multiplication with a constant, and since f1, f2, fk are homogeneous, this definition is okay, it's well defined. And the reason is that for a homogeneous polynomial f of degree d, let's say, and for a homogeneous polynomial f of degree d, fkx where some constant k comes out is k to the d degree of fx. So if fx equal to 0, fkx equal to 0, so this condition is independent of multiplying x with a constant. And okay, so this is well, later we will need the concept of smooth x. For now, we will define what it means x is smooth. So the basic idea, the idea is that we want. I will repeat some basic notions of algebraic geometry. Actually, I will repeat basic notions of algebraic geometry in the framework of complex geometry, and because sometimes it is easier to do that way. Okay. So as I said, later we will see what is the smooth, what it means smooth x, what it means the dimension of x, and so this we will see later. But for the moment, you can remember, you can put in your mind that dimension of Pn itself is this also. This capital N, and something also that at the end it is good to remind that actually the complex numbers, the field of complex numbers, we can replace it basically with arbitrary field. When we want to develop the theory of algebraic de Rham cohomology, you will see that at the end we don't need a complex number. It can be any field. And in this way, our theory will go into more arithmetic direction. And maybe another example that it is good to keep in mind is that the hypersurfaces. Maybe I write it here. Hypersurfaces in P. In the case of hypersurfaces, I will put this capital N equal to n plus 1. Maybe in a moment I will say why. And the hypersurface, it means that it is just given by one equation. It will be x in Pn plus 1, such that let's say I will take just one homogeneous polynomial fx equal to 0. And even so, I have not defined the concept of dimension, but you can by your intuition that comes maybe from analysis, that dimension of the hypersurface is n. When you have one equation, the dimension will decrease. And all these dimensions that you are seeing, they are actually dimensions of our complex numbers. So if you later we will see them as topological space and real manifold. So dimension as a real manifold, it will be 2n. But anyway, let's slowly we have to get familiar to these things. So okay. So as I said in the first lecture, the our maybe first 10 lectures are just we want to define algebraic theorem cohomology, this guy. We want to define singular homologies or singular cohomologies. They will be done in the same time. Singular homology, we will describe them. We will take elements delta, and from the de Rham cohomology, we will take omega, and this X will be for us this projective variety, and then we want to define these integrals. And starting from these integrals, or let's say periods, or then there is another old name, multiple integral. These are basically let's say modern incarnation of this old multiple integrals. And yeah, so this is as I said, this is the main the first main goal of the course. Once this is done, then we can explicitly say what is Hodge conjecture, what is and do Hodge theory. Okay, so we will start from the homology. So historically, the first homology which is created is singular homology, and by some reason I decided not to start from singular homology. Maybe so for this one, let's say singular homology, or this is there to call Cech homology or cohomology. And it is proved that both these homologies are the same. They are canonical isomorphism. Actually, all the cohomologies that we will dealing in this course, after tensoring with some proper field, they will be isomorphic. But okay, singular homology, if you want, in let's say in chapter, let me see. So let's say this. Okay, so chapter 4 of my book. It is about it's a kind of a crash course in singular homology and cohomology. But I decided to do with Cech cohomology, and after Cech cohomology, the plan is to do a study Lefschetz theorem for using Cech cohomology. And well, so for the Cech cohomology, I will go to the second book that I am writing with my pharma students. So today we are going to study Cech cohomology. But before now, I want to a little bit use these. Okay, maybe I make a kind of I ask a question. How many people have seen singular homology or Cech cohomology? Maybe just in the chat, if you want to write something for me, it would be good. So maybe let's say the question is, how many people have seen Cech cohomologies? So if some people want to write something in chat, if they have seen or they have not seen. So okay. Basics. Okay. Okay, so it is good news, because I see that many people have already seen. But I think we are going to define the Cech cohomology, and even so that you might have seen a Cech cohomology. Most of the time, the people they use it without computing it, and the base. I want to emphasize that in this course we want to take up elements of cohomologies and write them explicitly. And so I think it is worth to repeat the construction of the Cech cohomology here. Okay, so so the topic of Cech cohomology will be from I will tell it from chapter 2 of my book that I am writing with my former student Roberto Villaflor. Okay. So for us, X will be always this projective space, but Cech cohomology is done for arbitrary topological space. So for now, you get a little bit generalized. You take the generalized context, X any topological space. And maybe if you have done already topology, it is good to mention that we don't need the Hausdorffness of the space. So, and the main reason is that we will dealing with the topology with this projective space Pn with its Zariski topology. Again, if you have not seen Zariski topology, it doesn't matter. At some point, I will write down the Zariski topology. But just have in your mind that in algebraic geometry, the algebraic varieties, they are usually equipped with the Zariski topology, which is not Hausdorff. You cannot separate 2 points by open set, and this will not be essential for us. Okay. Okay. So since we are going to do Cech cohomology, it seems that one has to do few lectures for the concept of sheaf. But again, I want to emphasize that for me, sheaf is something that you can learn along the way that you learn mathematics. And for me, sometimes just making a few lectures just to transmit the idea of abstract sheaf does not seem to be necessary. So, so maybe okay. So, so whatever we are going to do is valid for sheaf of abelian groups S on X. And but we will not apply. We will our examples of sheaf will be very limited. So it's not. It's safe to just have in mind these examples of sheaf. Okay, for just the vague idea of the sheaf. Okay, so for the moment, this sheaf is something like that for any open set. Let's say non-empty. For any open set of X, it's associate abelian group. So we have this SU collection of abelian group FSU. It can be abelian group, it can be C algebra, it can be R module, for here R is a ring. And at the end of the sheaf, a collection of such object. Let's take the case of abelian groups. So it's a collection of abelian groups attached to open sets of a topological space. And when you have two open sets U and V, then you have then there will be this concept of a restriction from V to U. And of course, when you go to the books of sheaf theory, there will be some axioms of what this restriction must satisfy. And it's basically the mimic. It is the mimic of many properties that classical restriction maps satisfy. Okay, so we really don't need this to do general sheaf theory. So maybe let's go to, so as I said, this restriction map must satisfy certain properties, but we just need a few examples to carry in mind. And when I am talking about general sheaf, you can just simply replace these examples in your context, and then you can go ahead even without knowing the definition of a general sheaf. One sheaf that we needed, and actually it is a kind of trivial, it's called a constant sheaf. And for example, let's say for any ring, actually, like any ring of integers, these fields, which are also ring, are real numbers, rational numbers, complex numbers. And what is the sheaf of constant in this case? That usually one puts some x down. X, for example, there will, if you want zx, rx, let's say cx, sometime, and then in the rest of the lecture we will drop this x. And basically what it is let's say Rx. So we have to say that what is attached to open set U, what is Rxu, and it is just the ring itself. And okay, and all the restriction maps are identity. So this means that from SV was my ring R, SU is my ring R, and so all the restriction maps are the identity. And so this is actually, for now, I will just need this sheaf. This is a kind of trivial object, but the concept of Cech cohomology is done for arbitrary sheaf. Maybe another sheaf with non-trivial restriction maps is this structural sheaf of X. For now, I took X topological space. So, so the structural sheaf of X, I have to define this. This is denoted by OXU. The structural sheaf of U is what? For U, it is just a set of continuous complex valued functions in U, and this is just basically the set of continuous function from U to C, and of course if you have let's say V, open set V, if you have open set U, the restriction maps are just the classical restriction map of a function which is defined in V to U. So we don't need really to go into to the general definition of a sheaf. This is also something that you can learn along the way this course. What is a general sheaf, and slowly there will pop up many different other sheaves. And yeah, okay. So for now, I will need this. So for now, I will need this. This sheaf ZX, and as I said, I will just write it as Z. Remember that the objective is that to define these cohomologies. So for any sheaf we will define here, it will be any sheaf of abelian groups, but at the end we will replace with this one. And as I said, sometimes you drop X, so it is HNX, just write as Z. So So the next step is to define these these cohomologies. Okay, so let's do Cech cohomology. Okay, maybe I ask. Maybe I was a little bit fast. Any question? As I said, you can ask in any language that I understand: Portuguese, Spanish, even German, if my German is still good. Okay, so maybe this one for. So once again, I will start using an arbitrary sheaf of abelian groups S. But as I said, you can instead of S, you can put Z or real numbers, the sheaf of constants, real numbers, complex numbers. And if you have never seen the general concept of a sheaf, maybe let's just some notation. When we have element S of SU for S, a sheaf of abelian group, one usually call it section of S over U. And maybe another notation, global sections, the concept of global sections of S. It is just X itself is an open set in X. So there is abelian group Sx. So this is the elements of this guy are called the global sections of S. And there is another notation also. Another notation is gamma X S, and this is also another notation that it will appear soon. Reasonable H to H0 X and S. So these are, and yeah, okay. So now so as I said, we want to define this these abelian groups. And I will do it from let's say the section 2.3 of the book that I'm writing with Roberto. Maybe before going to the text, so as I said, we are interested on NH. These sheaves. Maybe again I will write, and later once we study the topology of algebraic variety, when this is algebraic, smooth algebraic variety, then we will see that these are just these are finitely generated abelian groups of any abelian, or let's say the same as Z modules. So at the end of the day, they will be isomorphic to Z, to something, some times this kind of torsion. Z divided by 1 and 1 Z times this torsion part. Z divided by NK Z, and this N1, N2, NK are just natural numbers. But in principle, for arbitrary topological space, they might get infinitely generated and so on. Okay, so let's. I realized that when I share my screen and this, I use my my camera. When it is recorded, the camera's screen is smaller. But any case, let's you know. Let's share the screen. Okay, just a moment. Meantime, if you have any question, let me know. The window. Okay. Okay. Okay, this is okay. So I found it a little bit strange to write exactly what it is written in the book that I'm writing with Roberto. So this part of the course I will try to explain directly in the text. Okay. Felipe, tá vendo o compartilhamento, não? O livro.
Sim, sim.
Tá. Okay, so okay. So the point is that we want to define this cohomology, and it has to do with the combinatorics of a covering of a topological space. So let's start from here. So as I said, we take X topological space, S sheaf of abelian groups. Again, you can take it Z. And most important, importantly, then we have to take a covering with UI of X with open sets. And sorry. And the idea is that the topology of X is governed by the combinatorics of how these open sets intersect each other. And okay, so we define this, let's say, this calligraphic U for the covering. So calligraphic U to the P will be the set of this P tuples, P plus 1 tuples of the open sets UI0, UIP. So remember that UP is the P plus 1 tuple. That's why our index starts from 0. And we are not really interested in the P tuples of open set, but actually we are interested on the intersection of this P plus 1 sets. So let's we define this let's say this support of sigma, which we denoted also by UI0 until UIP. It is just the intersection of all open sets. And okay, so the idea is that we want to define our cohomologies starting from this covering, and then at the end to get rid of the covering and to define something intrinsic. But during the course, we will see that it's not good to get rid of the covering, because all the computation that we will do in Hodge theory will be attached to some covering. That's why it is good to repeat this Cech cohomology here. So a p-cochain, what it will be just let's say, remember that this notation. Maybe I write it once again here. The point is that this writing is not good, but this is remember that this is the same notation of sections of S of in the support of sigma. I use this third notation that I was using. So this is So CP, the cochains attached to the covering U and with values in the sheaf S is this. You can take this one as product or as disjoint union. It doesn't really matter. You take this at let's say the product of all the sections of S on the intersection of P plus 1. Remember that this was the intersection of P plus 1 open set UI. And well, in the case of if you take this, let's say just if you take this, just this sheet is just Z. It is just to any intersection of P plus 1 set, you attach some integer. This is just this one. Okay, and okay. So before going ahead and using this kind of huge data to construct something, we want to get rid of let's say this P tuple. The idea is that at the end I am interested on this let's say this the intersection of UI0 UIP. Sorry, this is intersection of UI0, and so this means that if I want to be let's make a permutation of these indices. In some sense, I am making the permutation of the open set. So of course it acts. This permutation acts on UP. Remember that UP was just a set of these tuples. So you just permute the open set. So for this UI0 UIP, it acts just by permuting these indices. So it will give you this IP0 IPP, and you see that in the top we have we are using functions, or we are using sections of S over the support. We want that these sections also to be kind of independent of this permutation, but it's not quite independent, because you will see that at the end of the day, let's say when you take F in CPU with values in S, and so it, of course, you have this let's say you have this FP sigma, and then you have this F sigma. They are defined over the same open set, and the idea is that they must be different just because with the sign of the P. Maybe okay. Let me explain this one in the draft. Okay, so this part, the recording of this part will be small, but okay, if you want to look the webcam. So this condition is natural, because if I have UI0, maybe I stop. Okay. So if I have UI0, if I have UI1, and then I have let's say this let's say if I have F in S UI0 UI1, and if I switch, so at the end of the day, this F let me say in this way: UI0, UI1, U1, UI I1, I0. So attached to this one, I have one F. Maybe let's say, okay. Attached to this one, I have one F, but attached to this one also, I have another one, GS, and which are defined just in the intersection. And later we will see that since this is the permutation of 0, 1, its sign is negative. Maybe if you don't know, if you make Google of sign of a permutation, then you will learn very fast what is the sign of a permutation. But later we will see that it is natural to say that F at the end must be F equal to minus G. So we are not interested general collection of F and G. Rather, when we permute UI0 with U1, we want this that F equal to minus G. And whatever I was explaining, it was just let's say the general phenomena. Maybe again I start to let's say, okay. Okay. Felipe está vendo, não?
Sim.
Well, okay. So again, once again, as I said, when you define this CPU as this huge collection, at the end there are many tuples of sigma such that their support is the same. We want that all these sections of S to be related to each other at most by the sign of sigma, and that's why we restrict ourselves to this skew symmetric, elements, those that when we permute sigma, the F's are related to this one. And at the end of the day, we are mainly we are interested on this symmetric p-cochains, which are those cochains such that F is FQ symmetric, and this FQ symmetric is explained here. And yeah, and okay. Okay, this is the ingredient that we want to take it and define Cech cohomology. Okay, so something also that now we need in order to define Cech cohomology. So let's take sigma p+1 tuple. If you have p+1 tuple, then you can remove you can remove the j's element, and you will have p tuple. Okay, so this means that if I give you a p+1 tuple and j between 0 and p1, by removing the open set uj, I will get p tuple. And just by removing the G's open set of sigma. Since I have removed the open set, so this means that if I take the support of sigma, which was the intersection of all its open set, the support of sigma is inside the support of sigma j, because sigma j has a less open set. One open set is missing in sigma j. And since I have this one, then I have this this restriction map from from the sections of S on the support of sigma G to sections of S on sigma. Again, just if you can take S as integer. This means that if I have integer, I have taken an integer here, then you have I will associate the same integer here. So, or maybe if you want, take this structural sheaf of X, the ring of functions on S. So in this case, we have some non-trivial restriction. Okay, so then I will have this this restriction map from the bigger from this bigger open set to this smaller open set, and the next important concept is this the boundary map. Okay, so the boundary map is what is from okay here okay, and then we will put S here, the skew symmetric ones, but okay, from the p cochain to p plus 1 cochains, and how you define it. So if I take F elements here, so let's say if I take F here in this, I think I have to buy, okay, if I take F here in this as p cochain, then I have to define delta F. Okay, but what is a delta F? Delta F is a collection. By definition, it must be here. It's a collection of functions or sections of S in p plus 2 in the intersection of p plus 2 open sets or a tuple of p plus 2 open sets. So so this sigma will be what? This will be a p plus 2 tuple of open sets. Okay, I start removing open sets. So I have open sets indexed by G equal to 0, p plus 1. The sigma is indexed by this one. I start removing G equal, for example, I remove J. Then instead of p plus 2 open sets, I will have p plus 1 open set. Then remember that I use the notation sigma G. So when I remove it, I get sigma G. I can restrict F, which was defined in, I can evaluate actually F on sigma G because F contains functions which are defined in p plus 1 in the intersection of p plus 1 open set. And then I have then this one. Okay. Then and this is defined in this bigger open set. Now remember that now this I have restriction map. Then I can start restricting to the support of sigma, and you will see that we need this sign, and in a few minutes, and then I make the sum of all this, and it is for somebody who has never seen this this kind of definition, it might be strange. I think this is also natural, because Cech cohomology, first of all, it is invented after singular homology and cohomology. And remember that at least the first homology which was singular homology, we had intuition. And here you see that there is not too much intuition, except that we are dealing with the intersection of open sets and so on. But okay, I think this familiarity can be obtained a little bit trying to do some exercises and also returning back a little bit to the singular homology context. Okay, so at the end of the day, by this combinatorics of intersection of open sets and so on, we can define this operator. And okay, maybe one exercise that if it would be good to do in order to get a little bit familiar with this concept is that remember that I defined this skew symmetric, those which at the end they told me that it is good just to look for functions on the intersection of open sets, and it doesn't matter the order of intersection, and that's why we define the skew symmetric. And remember that the skew symmetric, let's say, skew symmetric cochains, it's a subset of the usual set of cochains. And so the one we have to show that this boundary map sends a skew symmetric elements to skew symmetric elements, because at the end we want to restrict delta over this the set of skew symmetric cochain. And okay, and from now on we can forget this delta. Otherwise we will focus our attention with this, putting some subindex S here and subindex. Oops, this is the point. So and then here from skew symmetric to skew symmetric. Okay, so another simplification when that we do it in the case of here, this boundary map. For example, this concept of a restriction, we will not write it. You see that here, this bar here is this is the notion of restriction to this open set. But for simplicity, we will not write this one. At the end, it is better to get used to this notation. And let's say some simplification that we will do it. Instead of sigma, we will try to do sigma as I0, the ordered set of indices, I0, I1, IP. So remember that I0 is, we have the open set UI0, I1, UI1, and so on. And so a p-cochain at the end will be a collection of of functions or constant, in the case of the sheaf of constant, fi0, fi1, fip. So it is defined where? It is defined over the intersection of ui0 with ui1, uip. And in the case of constant, the sheaf of constant, even we don't need to mention it is defined where. It is just a collection of constant. But in the case of a structural sheaf, we would have to carry in mind that this is defined over such open set. Okay, and and also over the boundary map. Boundary map will be we will simplify it in this way. So delta f So it's a collection of function attached to p plus 2 tuples of indices. So we have to determine what is this. Then just modifying the notation that we have. We take a sum over g equal to 0 until p plus 1. We remove j. So this notation that you see here, ij hat, it means that this is removed from the list of indices that I have. Once I remove it from my list, then I will have I0, I1, ij minus 1, ij plus 1, ip plus 1, which is a p plus 1 tuple. And so this means that I can use the element f attached to this p plus 1 tuple, and I can make the sum. And here there is a restriction to the intersection of ui0, ui1 until ui plus p1 that I have not written. And in the case of constant sheaf, I mean, we don't need it to write it. And then this is the boundary map. Again, this boundary map might look strange, but for this one, at some point, we will be back to singular homology, and we will see the boundary map in the case of singular homology, which has to do with really a boundary of something. At the end, the word boundary comes from the boundary of varieties and so on. And we will see that the name boundary comes from there. And okay, maybe so the idea that I want to make just 1 hour course, the rest just informal discussions if some people need. Okay, and so in order to define Cech cohomology, always these boundary maps they must satisfy this delta 0. There is here is again in some simplification. Maybe let me see if you see that delta is attached to number p. So this is actually delta p. Maybe so actually here delta is, one has to write delta p. And but usually we remove this p from our notation because it's possible it will not make a confusion. And for example, but what is written here is actually so we have this cp going to, I will not write the rest, cp plus 1. Oh, sorry. So this is the complex. This is cp plus 1, and then going to the cp plus 2, and then here we have delta p that I have not written delta, and I have written here also I have delta p plus 1. And so this means that the composition is the 0 map. And maybe if okay, maybe next lecture I will talk about a little bit the proof. The proof is very simple. Why this happens. And maybe one important factor also is that you will see that in the proof why we need this minus 1 to the g. At the end, the sum seems to be natural, but you have to choose, let's say, some sign here. If you don't put any sign, you will see that this proposition is not true. So I think during the construction of this Cech cohomology, the people have tried many signs here, and at the end they have realized that this is the things that you need to put here in order to get this property. And okay, so maybe before let's talk more about this proof next lecture. And at the end, the Cech cohomology, is in S. Then we have this this complex. So the notion of the complex is basically is this one. We have this sequence of maps, map from 0 to this one, then delta from 0 to C0 to C1, C1 to C2. And these are, let's say, these maps of abelian groups. And the basic property of the complex is that delta composed with delta must be 0. And why we need this property? Because you will see that when delta composed with delta is equal to 0, you take this kernel, and you can take this image map. So both these sets are in CP, and it turns out that this is the subspace of this one. And since it's a subspace, we can make the quotients, and then finally we can define the Cech cohomology. So this is the Cech cohomology with respect to the covering. We will, as I said, we will not use the abstract definition of Cech cohomology that I will tell in next lecture. We will always need to consider a covering because we want to do computation in Cech cohomology, and that's the reason we will keep the covering. But at the next lecture, I will mention that for certain good coverings, the cohomology is independent of the covering, and so on. So, okay. Maybe for the next lectures, maybe something that I will do it. Put some maybe some examples of the sphere. I told that our main example is the algebraic variety, but actually we need also the cohomologies of the sphere, and yeah. Just a moment. Okay. Okay, then, so something that I realized that for the topology of algebraic variety, that in my own book that I have used singular homology, and we need the concept of relative homology and cohomology. And so I will try to add more description of the relative cohomology that it is not included in this chapter. And yeah, I think this is for today. So the next lecture we will continue the Cech cohomology, and after getting familiarity with Cech cohomology, the idea is that we want to immigrate to my own book and there study the topology of algebraic varieties, Lefschetz hyperplane section theorem, and so on. Okay, so let's I stop recording, and then let's see.